Hello, this is day 2 of section 5.1 with Laplace Transforms. I thought we would pick up a little bit from yesterday and see how you did with the task that I gave you here of taking the Laplace of t to the nth power. So I'm just going to try and fill in real quick here. When we integrate by parts for this one, we're going to call u t to the nth, and we are going to call dv that e to the negative st dt portion. So du will look like this, and v like this. All right, so then using the formula to integrate this by parts, we would get that this, I'll just bring it down, the limit as a approaches infinity of negative t to the n over s e to the negative st evaluated from 0 to a minus our integral here. Okay. So basically what we get is this little portion right here. We see this similarity with some of the problems that we were working out yesterday, where it's e to the negative st. So when I plug a in, as a goes to infinity, a really large number, it's going to go towards negative infinity, which that exponential piece rules out kind of anything else in this case. And so, and then by plugging in 0, e to the 0 here, well, then, basically we get the whole thing is going to approach 0 as a goes to infinity. And so we're really just looking at this portion right here. And so if I bring out my constants here, just pull all that to the front, I get a positive n over s pulling out those constants. And then I'm integrating e to the negative st times t to the n minus 1 dt. Okay, this right here, we could keep going because we see that we have parts again, but obviously, we see a bit of a pattern. Okay, what we were originally integrating was exactly this, but t to the nth power, right? So this is just going to keep going. And so what we have to recognize here is this whole portion is the Laplace of t to the n minus 1. Okay, if what we had originally up here was the Laplace of t to the nth power, using our definition, then this is going to be, by definition, the Laplace of t to the n minus 1. Therefore, just back up here with the Laplace of t to the nth, this means that I can find the Laplace of t to the nth power by taking n over s times the Laplace of t to the n minus 1. Which means that if I'm evaluating the Laplace of t squared, that if this is the case right here, n is equal to 2. So let me just put this off to the side. In this one, n is equal to 2. All right, which means that the Laplace of t squared would look like 2 over s times the Laplace of t to the n minus 1, so just the Laplace of t. And this is where I refer back to my table, and I will post a good copy of the table for you, so that way you can use these shortcuts. And the Laplace of t would actually be 1 over s squared, if we remember that from yesterday's notes. So the Laplace of t squared, when all is said and done, is 2 over s cubed. Okay, we could continue this. So the Laplace of t to the third would be 3 over s times the Laplace of t to the n minus 1, which would be t squared. So that means I'm going to bring down my 2 over s cubed. And that tells me that the Laplace of t cubed is going to be 6 over s to the fourth. The Laplace of t to the fourth, then, just to continue, 4 over s times the Laplace of t to the third, which is that 6 over s to the fourth. So we get 24 over s to the fifth. So from this, we can derive another property here instead of using this kind of, this is a generative form of our formula. We have to generate all of the t to the n minus ones up to this point in order to find t to the nth power. So we are going to take this, use the pattern that we found, and say that because of this pattern, therefore, we can update our Laplace of t to the nth formula to be, if we look at our numerator here, this is n factorial. What I have done is essentially multiplied the number in the exponent, my n, by each of the lower numbers below it, because I keep multiplying by that previous. And then if we look at the denominator, we get s to the n plus 1. So what my n exponent is here, it looks like every single time I'm adding 1 to that. So this is actually a formula for Laplace of t to the nth where I don't have to know the previous n minus 1 in order to get t to the nth. Okay? All right, so that was yesterday's task. Today, I am going to post another video for you from Khan Academy. I think this one, it may be worth your time to watch this. Again, I'm going to let you make that call. What I'm going to do is I'm going to sum up for you here what formulas we actually get from the video. Okay, so basically the video derives the Laplace of f prime. And so the Laplace of f prime of t, which is important because we were talking about differential equations, so we should know what our first derivative looks like. All right, the Laplace of f prime is going to be equal to s times the Laplace of f of t, and then minus f of 0. So our function f evaluated at 0. Okay, this will be the transform for f prime to take that into our capital F function of s. Okay. The other thing it covers is the second derivative because we do some, second derivative systems here. So the Laplace of f double prime of t is equal to s squared. Okay, so s squared, and he derives this in the video, so you can watch this. So s squared times the Laplace of f of t. Okay, minus s times f of 0. And then minus f prime of 0. All right. So these two are very important because, like I said, when we deal with our differential equations, we have those first and second derivatives. So that's very important. Another thing, I can't remember if this is in the video or not, but another one that's very important is the Laplace here of your trig function. And again, I will post this, but the table that I've been talking to you about, referring to, I will post, and it will have cosine of omega t as well. So the sine of omega t, take omega over s squared plus omega squared. It's very similar to the cosine Laplace transform, so just watch out for that. So we're going to do an example here. This is kind of our first example of performing a Laplace transform. All the problems we've done up to this point have been just figuring out what the transform in general would look like. So we are going to find the Laplace of this, part polynomial, part exponential, part trigonometric function. Okay. Now, the way we're going to do this is we're going to take each of those terms that I just mentioned, we're going to kind of take them apart. And what we can do is we're really interested in the t cubed part here because that fits with that piece that we just talked about, transforming t to the nth power. We can pull the 3 out in front. So that constant in your Laplace transform does just get pulled to the front. So we're taking 3 times the Laplace of t cubed. Same thing applies with this minus 2. That negative 2 is going to get multiplied by the Laplace of e to the 4t. This is a transform that we talked about yesterday as well, e to the alpha t. And then we are going to add to that the Laplace of sine of 2t, and this is where we need the formula written above there, sine of omega t. All right. So t cubed, we can just go right back up here to our reference. T cubed, the Laplace of that is 6 over s to the 4th. So we transform that right away. 3 times 6 over s to the 4th. There's my transform onto a function of s. Minus 2 times the Laplace of e to the 4t. So let me bring that back real quick over to the side here. We said that to take the Laplace of e to the alpha t yesterday. We derived this one, and we said that that Laplace transform is equal to 1 over s minus alpha. So for our purposes here, alpha is equal to 4. And to perform that transform, it looks like I'm taking negative 2 times 1 over, maybe I should make this into a color as well, 1 over s minus 4. Okay, and then for the last one here, following the transform up here, omega is equal to 2. And so it looks like when we perform this Laplace transform that we get 2 omega over s squared plus omega squared, which is 4. All right, and then we would just do any simplifying from here. Sometimes that looks like getting a common denominator and putting them together. Honestly, I am perfectly fine with the solution 18 over s to the 4th minus 2 over s minus 4 plus 2 over s squared plus 4. That is a perfectly suitable final answer right there for that Laplace transform. Let me actually add on the end here, this is my capital F function of s after we complete that transform. Okay, so when you perform your Laplace transform, that it looks like that. All right, let me do a little time check here. All right, I'm going to do a second video that covers inverse Laplace transforms, equally as important for this section, but I'm going to go ahead and stop this video here and start that second one in a moment.